Well, hello and welcome to our webinar. My name is Tom Sandry. I'm the Director of Workforce Development at Vector Power. And in today's presentation, we are going to dig into the intended purpose and the theory behind the tan delta test as it applies to medium voltage electrical power cables. Now, tan delta, also called loss angle or dissipation factor testing, is a diagnostic method of testing cables to determine the quality of the cable insulation. Now, this is done to try to predict the remaining life expectancy and to prioritize cable replacement and/or possibly rejuvenation through silicon injection. It is also useful for determining what other tests might be worthwhile in order to predict overall health and condition and reliability of the cables. Now, before we get too far into this, let's start first with a little bit of an understanding of what is a dielectric material, like we see in electrical power cable insulation. Dielectric material refers to non-conductors or insulators in which an electric field can be sustained with a minimum dissipation of power. Unlike metals, no electricity flows in dielectrics when they are placed in an electric field. Instead, dielectric polarization occurs. Now, here we are going to see a charge being placed across a dielectric material. So, in essence, we form a basic capacitor, two plates of a capacitor, and we see a charge. Now, when a dielectric is placed in the electric field, electric charges do not flow through the material as they do in a conductor, but only slightly shift from their average equilibrium position, causing dielectric polarization. This produces an internal electric field, reducing the overall electric field of the dielectric. Now, considerations for dielectric materials. An important consideration for dielectric material is the ability to support an electrostatic field while dissipating minimum energy in the form of heat. This dissipated heat or energy loss is known as dielectric loss. The lower the dielectric loss, the more effective the substance is as a dielectric material. Another consideration is the dielectric constant, which is the extent to which a substance concentrates the electrostatic lines of flux. Substances with a low dielectric constant include a perfect vacuum, dry air, and most pure dry gases, such as helium and nitrogen. Materials with moderate dielectric constants include ceramics, distilled water, paper, mica, polyethylene, and glass. Metal oxides in general have high dielectric constants. Now, let's do a slight comparison of dielectrics to insulators. Dielectrics can develop an internal electric field which nullifies the externally applied voltage, while insulators do not develop an internal electric field. Dielectrics are easily polarized and can store charges. Insulators actively obstruct electricity. Dielectrics contain relatively weak bonds within atoms, and insulators contain strong covalent bonds. Dielectrics are mainly used in capacitors, power cables, transformers, and resonator oscillators, while insulators are used in high-voltage line systems and electrical appliances to prevent users from getting electric shocks. Let's start with another basic definition: capacitor. A capacitor is nothing more than two conducting plates with an area of A separated by a dielectric with a thickness of d and a dielectric constant of epsilon. So capacitance would equal the area times the dielectric constant divided by 4 pi times the distance between the plates. Now, Michael Faraday discovered that when the plates between a capacitor were filled with an insulating material other than vacuum, the capacitance would change. Dielectric constant is the ratio of the capacitance of a capacitor using that material as a dielectric, compared to a similar capacitor that has vacuum as its dielectric. The dielectric constant of a vacuum is 1. All other dielectric constants are referenced to this standard. Now, as we see in this slide here, given a certain area of plates and a certain distance between, the only difference in these two models is the dielectric constant of the material between the plates. In the first example, we see vacuum being used, a dielectric constant of 1, and here the capacitance calculates out to be 10 picofarad. Now, substituting air with oil, the dielectric constant is raised. Oil has a dielectric constant of 2.2. And we see by substituting oil for vacuum, the capacitance grows, even though the distance between the plates and the surface area of the plates do not change. Now, different materials will have different dielectric constants. We can kind of think of this as the basic ingredients in a recipe. So, for instance, vacuum, as we mentioned before, is kind of our reference. It has a dielectric constant of 1 by definition. Air, very close to vacuum, 1.000589 would be the dielectric constant. For all practicality, also dielectric constant of 1. Now, as we get into various materials, polyethylene or cross-linked polyethylene has a dielectric constant of about 2.25. Ethylene propylene rubber would also have a dielectric constant in and around the 2.27 area. Paper would have a dielectric constant of 2, mica 5.4, porcelain 7, oil 2.2, and water at 20 degrees Celsius would have a dielectric constant of approximately 80. So let's take this information and let's move a little deeper. Let's look at a typical insulation system. For instance, maybe in this model, this might represent a bushing, where the insulation is made up of porcelain, paper, and oil. Each of these materials form the recipe for the insulating system of the bushing, and each has a dielectric constant associated with it. So, if we were to mathematically add these dielectric constants, the insulating system, or the dielectric, would represent a dielectric constant of 0.894. Now, if we were to substitute air, for instance, oil is leaking from the bushing, so we are now substituting air as the dielectric instead of oil, the overall dielectric constant of the insulating system changes. Here, air having a lower dielectric constant than oil, the overall dielectric constant of the bushing now changes to 0.609. As a result of the dielectric constant going down, the total capacitance of the insulating system also goes down, and hence the total current goes down. Next, let's talk a little bit about dielectric loss. Dielectric loss is the time rate at which electric energy is transformed into heat in a dielectric when it is subjected to an electric field. The heat generated is given in terms of watts. Dielectric loss quantifies a dielectric material's inherent dissipation of electromagnetic energy. Again, example, heat. It can also be parameterized in terms of either the loss angle, delta, or the corresponding loss tangent of the angle delta. Both refer to the phasor in the complex plane whose real and imaginary parts are the resistive or the loss component and the electromagnetic field and its reactive, the lossless counterpart. A tangent delta or dissipation factor or even a power factor measurement circuit commonly views the specimen under test as a parallel capacitor resistor network. This equivalent circuit is repeated here, showing the various parameters of current with respect to the applied voltage V. So V is our test voltage. I sub T would be the specimen's total current. I sub C would be the capacitive or quadrature of the total current. I sub R would be the resistive or in phase, the loss component of the total current. C sub P equals the equivalent parallel capacitance of the insulation specimen. R sub P equals the equivalent parallel resistance of the insulation specimen. The resistor element of the equivalent dielectric circuit shown represents the watt loss dissipated in the insulation when a voltage is applied. R sub P represents that which is generally considered undesirable in a dielectric. It should be recognized that a certain amount of measurable loss is normal for most dielectrics, and therefore the existence of loss per se does not necessarily suggest an operating hazard. All right, let's take a look at a perfect capacitor. In a perfect capacitor, the basic properties are it passes no DC current, and the current leads the voltage by exactly 90 degrees. Now, perfect resistor. Current is always in phase with the voltage. So now let's look at relationships. Current, capacitance, and dissipation factor or power factor. In an ideal insulation system connected to an alternating voltage source, the capacitive current or I sub C and the voltages are in perfect quadrature with the current leading. In addition to the capacitance current, there appears in practice a loss current, I sub R, in phase with the voltage, as we see in this slide. In practice, no insulation is perfect, but has a certain amount of loss, and the total current, I, leads the voltage by a phase angle, theta. Theta would equal less than 90 degrees. Now, it is more convenient to use the dielectric loss angle delta, where delta equals 90 degrees minus theta. For low power factor insulation, capacitive current and total current are substantially of the same magnitude since the loss component, I sub R, is very small. Now, the power factor is defined as the cosine of theta, which equals the sine of delta, or simply equals the resistive current divided by the total current. And the dissipation factor is defined as the cotangent of theta, which equals the tangent of the angle delta, which equals the resistive current divided by the capacitive current. Next, let's go into and talk a little bit about types of deterioration in electrical power cables. Let's talk about thermal deterioration. Due to abnormal or high temperatures, we begin to see oxidation, decomposition, and evaporation occurring within the dielectric material. Now, this oxidation, decomposition, and evaporation creates reaction products such as ions, and the dissipation factor of the dielectric increases over time. We also see decrease in insulation resistance and a decrease in the overall dielectric strength of the material. Now, other types of deterioration we can classify as dry electrical deterioration. Now, this may be caused by voids in dielectric or voids in boundary, or by protrusions. The result of the voids create partial discharge, which begins to erode the dielectric, and this process continues, and we see a decrease in the overall dielectric strength of the material. Now, with protrusions protruding into the dielectric, we begin to see partial breakdown, and we see inception and growth of electrical treeing activity, which again in turn overall leads to decreased dielectric strength. Now, typical causes of dry electrical deterioration might be manufacturing imperfections, voids and contaminations that had occurred during the manufacturing or the extruding process, or it could be mechanical damage or craftsmanship when building the accessories such as terminations and splices. Now, another type of deterioration is a high density of small water trees. Now, many small distributed imperfections are caused by a spread of water trees and moisture absorption in the dielectric. This can lead to high density of bow tie water trees, which will increase the dissipation factor or increase the tan delta and decrease the dielectric strength of the material. Large concentration of water trees. These tend to be isolated imperfections due to moisture absorption, forming large vented water trees. We see an increase in the local electric field and electrical tree formation, overall decreasing the dielectric strength of the material. Another form of deterioration might come through chemical attack. Oil and chemicals. They can cause swelling, melting, cracking, and can form chemical trees within the dielectric material. This will increase the dissipation factor and will decrease the overall dielectric strength of the material. Now again, causes might be due to petrochemical spills, transformer, oil leaks, or fertilizers used in the agricultural area. Now, let's talk a little bit about the IEEE standard 400.2, which is the guide for field testing of shielded power cable systems using very low frequency or VLF. In the IEEE 400 standard, it talks about two types of tests. Type 1, which is simply a pass or fail, go or no-go style test. And we can see this performed using the very low frequency in the form of a simple withstand or high potential test applied to the dielectric material. Now, IEEE standard 400 also talks about type 2 tests, which are diagnostic in nature. Tests that are diagnostic in nature would be the VLF tan delta measurement, or the VLF differential tan delta measurement, or VLF tan delta temporal stability measurement. These are all described in the IEEE 400.2 document. Now, also in the document, we also have VLF dielectric spectroscopy, VLF loss current harmonics, VLF leakage current, and VLF partial discharge testing utilizing sinusoidal VLF waveform. We are going to focus on the tan delta diagnostic tests that are described in this document. And we will also describe how we can utilize tan delta measurements to perform what is known as a monitored withstand test. Now, if the insulation of a cable is free from defects like water trees, electrical trees, moisture and air pockets, etc., the cable approaches the properties of a perfect capacitor. It is very similar to a parallel plate capacitor, with the conductor and the neutral being the two plates separated by the insulation material. In a perfect capacitor, the voltage and current are phase shifted 90 degrees, and the current through the insulation is capacitive. In a real cable, however, there are dielectric losses in the insulation, and if there are impurities in the insulation, like those mentioned, the resistance of the insulation decreases, resulting in an increase in resistive current through the insulation. It's no longer a perfect capacitor. The current and the voltage will no longer be shifted 90 degrees. In fact, the shift will be something less than 90 degrees, and the extent to which the phase shift is less than 90 degrees is indicative of the level of dielectric losses and insulation contamination, hence quality reliability. This loss angle is what we measure and analyze in the tan delta measurement. The tangent of the angle delta is what we measure. This will indicate the level of resistance or loss in the dielectric. By measuring the resistive current to the capacitive current, we can determine the quality of the cable insulation. Again, in a perfect cable, the angle would be nearly zero. An increasing angle generally indicates an increase in the resistive current through the insulation, meaning contamination or deterioration. Keep in mind, however, that different insulation materials have higher or lower dielectric losses. Therefore, the angle or tan delta value may be higher for some insulating materials due to their dielectric losses. Now, we typically see this in electrical power cable insulation or dielectrics, such as cross-linked polyethylene versus ethylene propylene rubber. Cross-linked polyethylene has very, very low dielectric losses. Ethylene propylene rubber, or EPR, has much higher dielectric losses when compared to cross-linked polyethylene. Also, we need to keep in mind that the goal of tan delta testing is to provide a quality or reliability indication of an insulating system. In a cabling system, the terminations and splices are part of that system. If the insulation of the system and all accessories are free from defects like water trees, electrical trees, moisture and air pockets, etc., the cabling system approaches the properties of a perfect capacitor, as we stated earlier. Now, it should also be noted that in the event the cable circuit has transitions between multiple insulation types, for example, cross-linked polyethylene transitioning into EPR, the tan delta value will be influenced by the component with the higher dielectric losses. Now, in this example, EPR has a higher dielectric loss, and the circuit would need to be evaluated based on the EPR component. This obviously hampers the effectiveness of the test, since contamination that may be growing in the cross-linked polyethylene sections may be masked by the higher dielectric losses that are inherent in the EPR section. All right, so how do we perform the tan delta test? Well, when performing maintenance testing, IEEE Standard 400.2, Guide for Field Testing of Shielded Power Cable Systems Using Very Low Frequency, states that we perform the test in 3 steps, starting at 1/2 of the operating voltage of the circuit, phase to ground. This is expressed as 0.5 U0, or 1/2 U0. We then elevate the test voltage to operating voltage levels, or U0, and then to 1.5 times the operating voltage, or simply 1.5 U0. At each voltage level, we obtain between 5 to 10 tan delta readings. Now, at 0.1 Hertz, that would be 1 reading every 10 seconds. And in the IEEE 400.2, they talk about 3 basic criteria for the evaluation of the test data. First, the tan delta reading. In addition, the 5 to 10 tan delta readings obtained at the test voltage can be used to calculate the mean of the readings. The mean tan delta, or the average tan delta value. And here we can see the mathematic calculation. Now, we also look at the stability of the tan delta reading obtained at each test voltage. The tan delta stability refers to the variation of tan delta with time at a constant voltage level. The tan delta stability is defined as the measurement of the standard deviation of tan delta with time at a particular voltage, or U0. And here we would see the mathematic calculation of the standard deviation. Now, the IEEE 400 also talks about differential tan delta. The differential tan delta is taken by subtracting the average or the mean tan delta reading that was obtained at the 1.5 U0 test voltage by the mean tan delta reading that was taken at the 1/2 U0 test voltage. This is also sometimes referred to as the tip-up. And here we can see the mathematic calculation. Now, mean tan delta, differential tan delta, and standard deviation are all diagnostic methods of testing medium voltage cables to determine the quality of the cable insulation and the aging characteristics. Now, this is done to try to predict the overall reliability of the cable and the remaining life expectancy, and when we should be budgeting for cable replacements. Now, it should be noted that the test must be performed using a VLF instrument that is capable of producing a sinusoidal wave shape. We do not want to try to perform this test with cosine rectangular, DC step, or bipolar rectangular wave shapes. Again, the IEEE calls out a use of a sinusoidal wave shape when performing the VLF tan delta measurements. Now, evaluating test results. Now, when evaluating the test data, we need to first identify the type of insulation that we're testing. As we've already established, there is a difference in dielectric losses between cross-linked polyethylene, for example, and ethylene propylene rubber. But even within ethylene propylene rubber, there are different dielectric losses depending upon the different styles or types of ethylene propylene rubber. For instance, we have what's called carbon-filled or EPR black, mineral-filled, often referred to as EPR pink, discharge-resistant EPR, and also mineral-filled cross-linked polyethylene. Now, different types of insulation will have different inherent dielectric losses. And for this reason, we need to identify the type of insulation and the expected or normal losses associated with that type of insulation. Now, the IEEE standard 400.2 provides tables using historical figures of merit for condition assessment of service-aged insulation. Now, when we're using these tables, if all criteria for evaluation are within expected parameters, then no action is required. IEEE recommended repetition rate of testing for a healthy cable is approximately 5 years. Now, if the cable is outside of any of the expected criteria for evaluation parameters, further study is advised. Further study might be the use of partial discharge testing, for example. And also the repetition rate of testing is reduced to annual testing. So basically, further study implies that there is enough aging or deterioration to where we want to be testing this cable more often and reviewing the rate at which this deterioration is taking place. Now, if any of the evaluation criteria is well outside of the expected parameters, action is required. Again, action might be in the form of doing partial discharge testing. Action might also come in the form of cable replacement or budgeting for cable replacement. So let's talk briefly about the parts of an overall diagnostic program. There are various tests to check the cable. Tan delta is just one of many tests that can be performed on an electric power cable. The important thing is to select the right test for the right purpose and be able to analyze the results according to what you are testing. In other words, know what test you picked, why you picked it, and how to interpret the results of that test. So again, in our little model here that we see in this slide, we have tests such as partial discharge tests, tan delta tests, and withstand or high potential tests, sheath tests, and depending upon what problem we're hunting, the different tests will help us unveil what might be occurring in the cable. For instance, for splices and terminations, partial discharge testing is an ideal test to determine if there is any activities or deterioration and breakdowns occurring in the accessories. Within the cable itself, the tan delta test is an awesome test for determining if there is contamination and deterioration within the bulk dielectric of the cabling system. Tan delta tests can also give us indications of neutral corrosion. And for jacket integrity, there are totally separate tests that are referred to as sheath testing to determine the integrity of the jacket. Again, the key here is understanding the purpose and the theory behind each of the tests, understanding its limitations, and what that test excels at uncovering. Okay, Now that we have a better understanding of tan delta testing and the diagnostic value that it offers, let's look at how tan delta could actually improve a standard VLF high potential or withstand test. Now, a monitored withstand is performed by monitoring the tan delta, or you can also do this with partial discharge, but here we'll focus on tan delta, where we are going to monitor the tan delta values during the duration of the withstand time period. Now, if partial discharges and discharge channel growth activity is initiated during the test, the growth can be monitored so that the cable is not placed back into service in a weakened state. Now, this is a tremendous benefit over traditional high pot testing. In traditional high pot or withstand testing, historically we applied a voltage level to the dielectric. We set a timer for some prescribed time period. And when the timer went off, if the cable did not flash over, we considered it good and put it back into service. Hence what IEEE would refer to as a type 1 pass or fail, go or no-go test. Now, the Achilles heel with this test, however, is what is happening in the dielectric during the test time duration. What if there was a defect in there, but the defect was growing slowly, and the timer simply went off before the defect was able to go ahead and fault the cable? In essence, the very test that we performed to try to get an idea of what's going on with the cable inherently weakened the dielectric, and we then put it back into service in a weakened condition. And that has always been one of the fundamental flaws of the high pot or the withstand test by itself. By monitoring the tan delta value during the time duration of the test, we actually now have eyes that can see into the cable and see what is happening to the inherent losses as the test progresses. So, to kind of show this, I have on the upcoming slides an actual test that was performed in this manner. It was a high potential test that was performed, and during the course of the test, we monitored and captured the tan delta readings. So, let's take a look at what the results told us. Now, in the example that we see here, we started the test at a voltage level of 4.4 kV. So that was roughly 1/2 the U0 value for the cable that we were testing. And here we see, again, the test voltage, 4.4 kV. We see that the standard deviation across the 15 measurements that were taken was 0.01, and that's to the exponent of -3. So as we can see, it's very stable. Virtually no changes whatsoever in the tan delta value. And the tan delta value that we were getting was a value of 12.6. Now remember, it's a unitless measurement. It's merely a ratio of two currents. But also, the 12.6 is to the exponent of -3. So it actually would be 0.0126. But again, very stable at the 1/2 U0 test voltage level. Voltage was then increased in the second step of the test to 8.7 kV. Again, that would be the operating voltage phase to ground, or 1 times U0. Now here, we do see a slight increase in the deviation. Here, the standard deviation has gone up to 0.08. still well within the parameters of the IEEE 400 document and figures of merit tables. The tan delta value also slightly tipped up to 15.7. Now here, when we go above operating level and we increase the voltage to approximately 1.5 times U naught, or 1.5 times operating phase to ground, we begin to see some very interesting things happening in the dielectric. Here, the standard deviation has grown to 0.35, which is throwing us into the category of further study, further investigation, and actually beginning to borderline into the areas of action required. Also, we see, again, a rather significant tip-up occurring in the tan delta value. We now see the tan delta sitting in at around 22. So, again, in order to evaluate the delta of the tan delta reading, we would basically take this 22 value and subtract it from the reading that we obtained at the 1/2 U naught value. Once again, when we do that, we see that the level of tip up or change in tan delta is putting us into the action, putting us into the category of further monitoring, further testing is advised category of the IEEE tables. Now, after we went to the 1.5, we then raised it to what was to be the withstand value. And at the withstand value, the test was to continue for a time period of 30 minutes. Now here, however, we do see at the 16 kV level, the standard deviation has significantly increased and has definitely put us into the area of action is required. Now here we see that value at 2.18. So the cable is actually getting weaker as we've been raising the voltage, and particularly here over the course of time, we are seeing another effect taking place. Notice the voltage is not changing, but the tan delta reading is slowly beginning to increase, indicating weaker dielectric strength, higher losses or higher resistive currents flowing. In essence, we are watching the growth of a defect. Stopping the test at this point, we would be putting the cable back into service in a weaker condition. And this is really good information for when we are performing tests on electrical power cables. By monitoring the tan delta values or by monitoring partial discharge activity, if we do begin to see the deviation level begin to grow, we can immediately stop the test. We can have dialogue with our client and basically explain the reason why we stopped the test. We began to see deviations occurring, indicating the possibility of a defect beginning to grow. By stopping the test, we've concluded the test at as close to an as-found value as possible. We have not further deteriorated. We have not grown this defect in any way. So if we would have to put the cable back into service, we can do so without putting it into a weaker condition than when we have found the cable or the as-found condition. Now, if we do choose to continue with the test, then the decision needs to be made that we continue monitoring the tan delta value as it begins to grow. We are no longer subjected to the timer. We are now going to watch the growth and bring it to the point of failure so that we can locate the failure, render the necessary repairs, and put the cable back into service in a reliable state. So again, here we can see that growing tan delta number, even though the test voltage is not changing. And that is going to conclude our webinar for today. We enjoy putting this content together. We hope that you find value in it. And for our YouTube channel, please, if you like this content, hit subscribe, click the notification bell so that you're notified as to all of our up and coming webinars. Thank you again for your attendance.